So in this case, we are going to consider another example of our superposition theorem. If you are to consider this, you are asked to calculating a network using a superposition theorem. A network is configured as shown in Fig 1.11, that is A, which is a network with 5 resistors. And from there, we are asked to calculate the current and also the power and the voltage through the 7-ohm resistor. And the 7-ohm resistor is the load resistor in that case, using the superposition theorem. So if we are to consider, from our previous case, I talked about this superposition on an introduction where we need to determine the currents separately. So definitely, according to the V1, we're going to have the currents flowing there from the supply. And according to V2, the current is going to flowing from the V2, which is I2 like that. These currents, they are going to be affected by so many resistors, talking of this one from I1. Until it reaches this point, it is going to be affected by this resistor. But at the end, we will have this current here. On the other hand, from this other side, we can see that according to this I2 that we are seeing, and also other resistors that will be affected, because once you'll be working, other resistors will be there also. So all those resistors, they are going to affect us until we reach to this current. There are resistors also that are affecting I2 there. So you combine those currents that we are seeing. So how are we going to obtain this current and also obtain this current? It is when these circuits or when these voltages are taken separately, the sources. So like I said, you need to short circuit one of these, that is to work with them separately. You can even work with V2, short circuit that, or you can start with V1. It's up to you. So let us just short circuit V2. The moment that you short circuit V2, you replace with internal resistance R4 in that case. So you're going to replace with what? With R4, which is the internal resistance. All right, so meaning to say our circuit was going to look like this, okay? Let us just see how we're going to have at the end. It is best that you also have a separate diagram that you can also understand how these resistors are connected, or how this network is going to be connected. So this is what you're going to have, something like this. Remember, we've got R2, R3. The load resistor is going to be here. We've got our load resistor. Then it is going to be what? A short circuit here. It's just going to be continuous, meaning to say we have R4 in that case without the voltage. So it's just going to be a straight line. That's a short circuit. And we have got our R4 in that case. So this is how our circuit was going to look like. All right, so let us just see what we have. That's our V1, 10 volts. This is our R1, guys, which is 6 ohms, 10 ohms for R2. And we have got our R3, which is 12 ohms, our load resistor here. That is where we have got our load resistor here, the 7-ohm resistor. Remember, this is no longer there. And we have got our 13-ohm resistor representing R4. All right, so this is our R4, which is 13 ohms, like that. So this is what you're going to have. I'm just going to call this diagram 1. Okay, so that in any case, we might need to refer it back. So I'm just going to call this diagram 1. From our diagram 1, we can see that, or we can, analyzing here, we can see that we need to calculate the current across the load here. So let us just call this IL1, okay? Since this is our first calculation that we are doing, how can we reach to this current? It is now in our hands. Like, how can we reach to determine this? If we can determine the supply, remember this is where the supply current, the supply voltage is. So when you say the total current I1 is going to be here. I1, like I said, is going to be affected by a number of resistors until we reach to this point. So this I1 here is affected not by this resistor, by all of these resistors in this network, because I1 is representing the total current. So if I1 is representing the total current, therefore it is affected by all the resistors, in the network. So meaning to say, in this network, we need the sum of these resistors, the total resistance. But how can we calculate the total resistance? Now that is where we have to apply our Ohm's law, this and that. Okay, if we consider properly, we can see that here there is a parallel combination. If you check these two, they are in parallel. After combining these that are in parallel, there is a series resistor R3. So since you are considering the total resistance, guys, I'm just going to take here, I hope you understand the series parallel. It can be easier to explain this one. It's going to be series to a parallel combination. So let's combine these first from, so we need total resistance in this case. So find RT. So before that, like I said, we're just going to take from R3 here to this one. Let's just combine these. You can do the way that you want, guys. You can combine these two, that is in parallel. You add to this one. You draw your circuit, guys. It's up to you. It's up to you. So in this case, you can combine because already this current is there in this. It's going to be shared. The current here is part of this. So it's going to be shared. Sharing this current, you see that it is affecting these resistors together. So that is why I'm saying instead of you working them out separately, you can just combine. So in this case, I'm going to take from, I'm going to combine R3, RL, and R4. All right, let's start with this first. So if we check from R3, is going to be connected. So let's just call this R, just going to say R is equal to R3. Then these two, they are in parallel. So you're going to use product over sum there. So you're going to add the product over sum of RL and R4. So that's RL plus R4 like this. So this is going to give us, this is the combination of R3, RL, and R4 combined together, guys. We just need to combine this, which you can work the way that you understand them. So that is going to be 12 plus these two, product over sum there, that's 7 by 13 over 7 plus 13. That's 7 plus 13. So if you had to combine, that was going to give us 16,55 ohms. So this is not the total resistance. This is the resistance after combining R3, RL, and R4. So this is what I want you to see now. This network is going to be actually identical to this. If you've combined these, you are going to see that, like I say, this is our diagram 1. So let's have our diagram 2 here. So our diagram 2, after combining these, I want you to see what's going to happen. You'll see that it will be the source as it was before. This one, you're going to take this part, also your R2, but you have combined these ones. It's now a single resistor, this one, which is the one that we called R, this one. So it is now like this. It is just a single resistor. You combined all these three. So that is where we have our R there with the 16,55 ohms. And this being our V1, 10 volts, our R1, which was 6 ohms, our R2 in this case here, which is 10 ohms. That is what we have. These ones, they are represented by RL, by this R, sorry. So if we are to say they are represented by R, let's analyze now according to the currents, because this is I1. We can at least fill in these currents to say, okay, I1 is going to affect one, another current is going to flow here, which is in this branch. We can even call it whatever way that you want. You can even call this IX, or you can even call it I2 according to this diagram, not like I2 of that network, original network. Then there is this current that is flowing here in this resistor. We can call it IR in that case. This one is the most important current because, as you can see, this current IR here, it is the one that is at this point here, because this is a combination of these two. Okay, let me show it from the diagram here so that we can understand. Okay, remember I said this is IR here. You can call it the way that you want. You can name this current the way that you want. This current that is at this point here. This current here that we are seeing across this resistor, since these two resistors, these three resistors are connected together, it is the current here that is flowing at this point. This is your I1. I2 is entering here. This is I2, this one. This is your I2. This IR is the remaining current, this one that is at this point. That is where we have this IR that is going to be shared. Another one flowing into what? The load resistor. Another one flowing in this. So once having this current IR, this one, once we have this current, it is now easier for us to calculate the current across what? The load resistor, which is this IL1. This is the one that we want. So how are we going to obtain this IR? That is the question. Okay, like I said, you can name that current the way that you understand. So in order for us to obtain this, we can see that we still need to obtain the total voltage, the total resistance, so that you can obtain this I1. Remember from your previous diagram that we had from our introduction, we can calculate this because this is a parallel series combination. So we can have the total resistance from there. So remember we wanted RT. So now we can have our total resistance. So that is here. Our RT now can be calculated. So RT is going to be the parallel combination from those resistors that we combined here. They are now in parallel with R2. So that is going to be R times R2, the product over sum. Then we add R1. Okay, so we're going to add R1 like that. Thus, we've got the total resistance. So that's the product of these two, or you can even say R1 plus the product. It's up to you. You can even write R1 6 plus the product over sum. That is going to be 10 times 16,55 divided to the sum 10 plus 16,55 like this. So there we are going to have the total resistance, which was going to give us 12,234 ohms of the whole circuit. This one, we have the total resistance. So guys, having the total resistance from this diagram too, you can calculate the total current. So in this case, we're going to calculate the total current, which is equal to what? Which is represented by I1. So the total current is represented by I1. So that means we can calculate I1. I1 is equal to what? Voltage over the total resistance, because that is the total current of the circuit. So it's the total voltage, which is V1, over the total resistance. So V1 is 10 over the total resistance of 12,234. So that was going to give us I1, which was going to be 0,817 amps. So having I1, let me indicate it on the diagram so that we can properly see what I'm saying here. If this current here is given 0,817, we can calculate this IR, this one. Remember, it is the one that we need so that we can calculate this IL1. So how can we calculate this IR? We can call it the way that you want. You can call it I2. You can, guys, it's up to you the way that you're gonna call this current. In order for us to calculate IR, we can use the current divider rule. So let's calculate IR in this case. Calculate IR. Using the current divider rule, we see now the importance of that current divider rule. IL, which is, this I1 is the supply. It is supplying this. It is divided like this, as you can see. This one entering I2, another one entering this other part, as we are focused on this, which is this one part of IR. So using the current divider rule, we can calculate that IR is going to be the opposite resistor. Remember I said use the opposite resistor, so it's going to be R2 over the sum of these two resistors times what? Times the supply current that we have, which is the total current, which is I1. Remember, our total current is I1. So meaning to say IR was going to be R2, which is 10 over the sum of these two resistors. That's 10 plus 16.55. Then you multiply to the supply current, which is 0.817 amps. Okay, this is 0.817. So that was going to give us IR, which was going to be 0.308 amps. This is what we have as the current that is going to be subdivided here. So if you take it back, now you can understand from this diagram here. We are saying there is a current here, IR here, this one. This current IR, because is the one entering the combination of these three resistors. That's why it is from this 16.58, the sum of those three resistors. So it's already taken among these three resistors. So meaning to say there is a current here. The current that is flowing here is the same as the one that we'll see here at the end. So that is at the end, there is a current there, which is 0.308 amps, which is at this point here. So we can use our current divider rule to calculate the current across the load from diagram 1. We can see that from our current divider rule, this current is now subdivided, as we can see at this junction. Another one is going to be entering here, which is in the load. Another one is going to be entering R4. These two currents are divided from IR, which now acts as our total current. So it means we can calculate the current across the load by using, remember, current divider rule, the resistor opposite, which is R4 on top. So that is going to be R4 over the sum of these two. So that's going to be RL plus R4 times the supply current, which is our supply current in this case, is our IR. So that's it. So we're simply going to substitute our R4 in this case we are already given, which is 13 from our diagram. So that's 13 over the sum of these two, the 7 plus 13, the R and RL. Okay, the RL and R4. Then you multiply it to the supply current entering those two branches, which is 0.308. That was going to give us the current across the load, which was going to be 0.2002, something like that. So you can even just save it as 0.2 like that amps. To 3 decimal places, just going to be 00 like that. You can use those values as they are. It's still fine. So look how our superposition, guys, can be like. We are not yet there. This is from the first one. You calculate all these using the idea that you understand from your network theorems that you have done before, the laws that you have done before, considering to say you are working with the Ohm's law, this and that, current divider rule, everything is going to be needed. All right. So with this, we are going to put it aside so that we calculate the other part. Remember, on this diagram, we calculated this with our V2 being short-circuited. So this is what we got here, which is 0.2 amps. That is IL1. So let's have the same thing, but now with another voltage as a short circuit, which is V1. Remember this one, it was for V2 where we calculated this one. So we're gonna consider this time we have to short circuit V1. So if you started with the V1, it's fine. It's up to you. So if you short circuit V1, you replace with the internal resistance there. So you're gonna replace with what? Replace with R1. So meaning to say, this is just going to be a continuous line. Everything is going to remain as it is. Okay, so every other part there is going to remain as it is. Going to have our resistor 1, okay, to the R2. Okay, that's where we have our R2 in that case here. Then to R3, everything, guys, is just going to remain as it is to R3. Then to the load resistor. Okay, to the load resistor, which is this part. Then to the V2, which is now the supply of the circuit this time. So we are now considering V2 as the supply. So this is how it was going to look like. So meaning to say you have to analyze according to this circuit now. With our R1, which is 6 ohms. All right, let us just quickly have this R2, 10 ohms. Our R3, 12 ohms. Okay, let us just have this, which is 12 ohms here. The load resistor, 7 ohms. This is our R4, which is 13 ohms, and our V2, which is 16 volts. According to this, I2 is in charge now. It is flowing this direction according to the positive side. So that it means this is our I2 that we are focusing with. And this I2 is supposed to help us to determine the current that is going to flow across the load. According to this I2, it's going to be like this, which is the current across the load. We need to determine this, just like how we determine this one. So how are we going to determine this current? With these resistors in this network and how it is connected now, how can we obtain that? All right, let's consider what we are seeing in this situation. We can see that we have got a parallel combination because we need the total resistance in order for us to have the total current, which is I2. We need the total resistance. So from this side, R1 and R2, they are in parallel. Then we combine to R3, they are now in series. It's going to be series. So it's going to be parallel plus the series. So just like the previous, let's just combine this part. As you can see, this has nothing to do with RL. So let's combine it like that. So in this case, just combine R1, R2, and R3. So by combining this, like I said, we're going to have the parallel combination of R1 and R2. So these two are in parallel, product over sum. So that's the product over the sum of the resistors plus R3. So you're going to add the R3, which will be a series combination. All right, so we need to combine these three first and see what it's going to look like, okay? So let's multiply these two, 6 R1 and R2, that's 6 by 10 over 6 plus 10. Then we add R3, which is 12. So that was going to give us the resistance, the combination or the total resistance of these three resistors that we are seeing with the parallel and series combination, which was going to give us 15.75 ohms. With this, Let's say this is our diagram 1 according to the way where we short-circuited V1 with this V1 as a short circuit. Let's say this is our diagram 1. We are going to notice that these three are now a single resistor, which is this R. Okay, let's have it as a diagram and see how it's going to look like. These three resistors here combined together, they will look like this. It's just going to be a single resistor. The combination of R1, R2, and R3. This is the one. Meaning to say we're going to have the load resistor. It's not going to be affected. The load resistor is going to remain to the supply, which is our V2 like this. This is what we have to the supply. So guys, the way that you answer there is in your hands, the way that you're going to answer there. So this is the combination R there of those three resistors here, these ones, when we combined them. So that is our 15,75, this one, 15,75 ohms. And we have got our load resistor here. Our RL does not change, 7 ohms. Okay, that's 7 ohms. The rest of the circuit as it is, the rest of the circuit, the V2, the 16 volts, and the R4, which was 13 ohms. It's not going to change this one. So this is where we are. Just going to, like I said, call this diagram 2. Okay, since this is 1. According to the diagram 1, we saw that I2 is this one. This is the supply. This is what we have here. This is where our I2 is, and it's not going to change. And the current entering the load resistor also is not going to change. This is where it is. And this one is the rest of the circuit. From here, after here, the rest of the circuit combined together here, the rest of that circuit, which you can even call it IR, which is affecting those three resistors combined, R1, R2, and R3. So the question is, if we have the total current here, can we calculate this direct? We can calculate, this time we can calculate direct. There is no need for us to calculate this IR. No. We just need the total current. And we can use our current divider rule. Remember from our current divider rule concept. So we are limited now to the total resistance. That's why now because we know that we need the total resistance. In order for us to have this current, we need the total resistance. So from that, let's continue. Remember, this is the combination of the three resistors. So therefore, what was going to be our total resistance from this circuit? Our total resistance was going to be what? These two in parallel, in series to this one, just like what we had here. Parallel in series. This is exactly parallel series again. So meaning to say we are going to have R and RL in parallel. So that's R times RL over the sum. That's in parallel plus the series, which is R4. So let's combine this. That's the product over sum 15,75 times RL, which is 7, over the sum 15,75 plus 7 plus R4, which is 13. So with this, we were going to obtain now the total resistance of the circuit of this combination, which was going to give us 17,846 ohms as the total resistance. With the total resistance now, we can be able to calculate the total current. Remember, the purpose is for us to obtain, is for us to have what? The total current. So here, guys, this was from the previous calculation. It is for us to obtain the total current. And what is representing our total current according to this circuit diagram? It is I2. So by calculating I2, you are calculating the total current. And how is that possible? From the total voltage over the total resistance. So that is over the total resistance. We can calculate I2, which represents the total current. Our total voltage is 16. the total resistance, which we calculated, and we got that as 17,846. That was going to give us I2, which is representing the total current of this network, which was going to be 0,897 amps. So there we have got I2, which is the total current. So if this is the total current, guys, let's take this total current to our circuit diagram here and see, is it going to help us to calculate the current across the load, which is the one that we need, or we need to calculate this one? Okay, let's see. This is where we have our total current I2, which is 0,897. According to this, we can see that this is the same current that is entering here, IL, and also IR. So it is divided on these two. So meaning to say current divider rule can be used to calculate this IL2. So with this total current, guys, we are now going to calculate the current across the load. So the current across the load can be calculated from the current divider rule again. So meaning to say the current across the load in this case, because I2 is the total current that is feeding these two. So they will be taken. Like I said, if you want this, you use the opposite resistor. Not this one. I2, you're talking about where it is entering, where is it feed, where is it going? It is these two resistors. So it's going to be R on top. So that is going to be R over the sum, R plus RL times the total current, which is being supplied. So that was going to give us the load current, which is R is 15,755 from those calculations that we made. So you see now the purpose of redrawing these diagrams in smaller, because it can help you now to say, okay, this one I can simply calculate direct. Okay, over 15,75 plus RL, which is 7 times the total current, which is our I2 of 0,897. So that was the idea of the question. You can have now the load current I2, which is going to be, in this case, sorry, it was going to be 0,621 amps. So we calculated this from a combination when V1 was a short circuit. We now have this. So we can bring it back to our diagram. Here, remember, that is where we have our IL2, this one. So all these guys is no longer important. All these part that we had, now we have to superimpose and finish up everything. So that is our IL2 here. We got 0,621 amps. So if we superimpose from the first combination where we had our V2 as a short circuit, that is the current across the load was going this way. So therefore, the current across the load is going to be the sum, because these two, they are going the same way. Okay, this one is going down. This one is also going down. So you have to add, like I said here. They are going the same direction. So you add. So it's going to be IL1 plus IL2 across the load. IL1 we calculated before, guys. Remember, that's where we got 0,2. IL2 we calculated recently now. That is where we got 0,621. Remember, this was 0,2002. You can even use it like that. It's up to you. Okay, or you can just use it at 3 decimal places. Remember your instruction, so it end up as what? As 0,2. All right, so adding this, it was going to give us 0,821 amps. So that is our load current after superimposing. After superimposing everything, after combining these currents across the load, because we are talking about across the load. If they wanted any other branch, you're going to work with that branch. So that is why we focus what is the question on. You can focus with where the question is about. There's no need for you to be calculating each and every branch. Answer the question. All right, so that was our first part of our question, to calculate the current across this load resistor RL and the power, then the voltage. So guys, we have across the load resistor, we have got the current. So you can calculate the power, guys. We've got the resistance. Remember, the resistance is 7 ohms. The current is now there. This is the combined current. Not these ones were separated currents. So we combined them now. It's now this. So we are using the combined current there of that branch of the load, which is what? The load current that we're given there. So power can be calculated, guys. We have got current and resistance. How do you calculate power from there? Power from current and resistance, that's I squared times resistance. So meaning say the power across the load resistor is going to be, that is IL squared times the load resistor. That's the idea there. We have the current, that's 0,821 squared times our load resistor, which is RL, which is 7. So that was going to give us the power, just like that. So meaning to say, the power in this case was going to give us 4,718 watts. Then the voltage also can be calculated. We have current, we have resistance, not this one. This one, remember, it was the subpart. I'm talking about this supply current, I mean the load current, this one of the one that we calculated as the load current. There's a current, there's a resistance there. So voltage also can be calculated. So it means the voltage across the load, we're simply going to use the current across the load times what? The RL. Or you can work from the power you divide, but guys, we have got something that is already there. Current is already there. 0,821. The value of the load resistor is 7. That is not going to change. So that was going to give us 5,747 volts to 3 decimal places as the voltage across what? The load resistor, which you can also just write as VL. You can write even this one as PL. The way that you indicate, guys, is up to you. You can even write this as IRL1, IRL, like the guys, the way that you write there is in, is the way that you understand it. So that's, we have it, everything. So after calculating the currents, you can even be asked to calculate power and voltage. So let's revise as many questions as we can, preparing ourselves for the exams that are ahead of time. As you can see, it's very, very important. Each circuit is considered separately when working with superposition. Then you superimpose at the end. How are the currents related in that network, in that branch? How are the currents taken? So, like I said, we're going to have more questions also working with other theorems so that we cover up our syllabus as well.